Thank you very much. It's good fun to be back at conference and speaking. So this talk is mostly about microservices. It's going to look at what microservice architecture is, why you might want to use it in your software applications, and some of the common pitfalls you might sort of run into while implementing microservice architecture. It's broadly split into two sections. In the first section, I'm going to go sort of over and give an overview of what microservices are and have a look at some of the common problems that I've encountered in various systems I've worked with on the past. And then in the second section, I'm going to sort of go into a bit more detail on like a slightly different way of doing microservices to what a lot of people do, which can help alleviate a lot of the problems that we see in the first section. So start off with microservices. You've got kind of two contrasting architectures, if you like. You've got your big monolith, which has just like maybe a single code base, or maybe one or two, but usually like one big code base. It'll possibly talk to one or more databases, but generally the entire thing is one package. Whereas if you contrast that with a microservice architecture, what you will typically have is lots of smaller services that each do a small task. Each one will probably have their own data store. They might not necessarily use the same technologies in all of them. And so you've got like a bunch of different services, and then either your browser front end will talk to different services, or you'll have some sort of aggregating service which will be able to route, like an API gateway, that will route requests through to the different services. So the key features, if you're thinking what you're looking at as a monolith, it's a single app that contains multiple different business functions. Now, as I say, in general, you'd probably just have a single monolith if that's the route you're going down. And it quite often, I mean, a bit less these days, because microservices have sort of shifted a bit more out of favor and back towards a monolith. But certainly when I started giving this talk a few years ago, people saw monolith as like a kind of a derogatory term sometimes. It's like a big sort of unorganized mess. But it's perfectly possible to design a really well modularized monolith that works really well, just as it's equally easy to design a really bad microservice architecture, which is just as equally bad as the monolith. Another thing is, I think one of the big differences is that when you have a monolith, you tend to deploy it and scale the system as a whole piece. This is a little bit less troublesome with a PHP application, because of the way PHP works, every request you throw everything away and bring everything back up. So microservices are much more common in things like Java and Go, where you have a single binary and you have to load the whole thing into memory to get everything running, because it means obviously if you get a traffic spike, scaling up means that you have to have lots of big servers, whereas if you've got a lot of little services, you can allocate resources more effectively to just the parts of the application which are under load. Another thing that you'll see is, because you've got a single code base, you're typically stuck with a single technology stack. So everything would have to be in PHP or in Python or in Java. So you have to pick a tool that is good for the general purpose, and that stops you from like moving into something that is specific and good for a particular use case. We contrast that with the features of microservice architecture. You will typically have a group of services, and each one of them will handle a single business function. If you consider like the Unix philosophy of having small tools, where each one does a single thing really well, and then you are able to combine those tools together in order to actually produce a result. Same sort of thinking happens with microservices. You have lots of different functions which are separate, and then the combined set of them actually produce the results that your system needs to do. It should also have like complete autonomy over its area of responsibility. So you should group everything that's similar together and sort of not have them talking to lots of different places to do the same thing. Microservices should be independent. So there's several ways in which it needs to be independent. First of all, in contrast to your monolith, you should be able to deploy your microservice independent of the others, and it should run, all the tests should pass. It shouldn't depend on any of the microservices being up and running. You should be able to scale it separately, so that if you've got a burst of traffic to registrations, you can scale up your registration service and leave the other services alone and save potentially on your rather large AWS or Google Cloud bills. And you should be able to change entirely how a microservice works without impacting on other ones. So provided you have like an API or something like that, you can change the code behind it. You could even change from PHP to a different language, and all the other microservices shouldn't notice the difference. Microservices need to have some sort of defined API in order to interact with them. You will typically have a system where you've got a lot of services and they will need to collaborate at certain times. So you need to have an API that's defined as how you interact with each microservice. Quite often, the choice that people reach for is a REST API, but don't feel that you're constrained to that. It doesn't have to be a REST API. It doesn't have to be a HTTP API. You could perfectly happily build a microservice which accepts syslog formatted packets on a particular port and use it to parse logs and do alerting and things like that. That would be a reasonable API for a logging microservice. And another feature is the idea that you have smart endpoints and dumb pipes. Now, there are some sort of former attempts at service-oriented architecture where you would build a lot of intelligence into the routing between your services. So you might have queues which route messages to different places, that process and transform messages between services, and you have a lot of logic built into the connections between them. By comparison, in a microservice architecture, the actual logic, the smarts, should be in the microservices themselves and not in any of the sort of glue layer between them. So let's talk about microservices. So let's have a look at some of the advantages. First one is it allows a diverse technology stack. And I think this is one of the things that people don't necessarily make as much use of as they could. But if you're building PHP and you've got a bunch of microservices, you might find that there is a use case where Python or Java or Go fits a particular niche application in your business much better than PHP does. Having a microservice architecture allows you to take advantage of that and keep most of your services written in PHP, but leverage the functionalities that might be available in other languages to deliver a specific solution to a specific problem. I've touched upon this a few times already, but probably the advantages, the biggest advantage of microservices is the independent deployment and scaling. That allows you to sort of tackle hotspots more efficiently than if you had a monolithic architecture. You also end up with a smaller code base. So because each microservice is small and focused on a particular task, the amount of lines of code in each individual service is much lower, and it's much more focused on the task. That means that if you bring in new developers or just shift people around projects, it should be a lot easier for someone to get in and understand where the bits of the code are that they need to talk to and what they need to work with, because there's less distractions, there's less other things that they have to go, oh no, that's not relevant to my particular problem that I'm working on now. Another advantage of a small code base is if you've got a microservice that isn't doing the right thing and it's only a few thousand lines of code, it's much easier to justify throwing away the whole code base and starting over with something different that works better for you. Obviously, if you've got a huge monolith, that probably represents years of accumulated work, and to rebuild it would take a similar amount of time. If you've got a small microservice that's doing a very small function, possibly the time to build a complete replacement from scratch might be a lot shorter. Obviously, every kind of architectural choice comes with disadvantages as well as advantages. And probably the key disadvantage on a microservice architecture is availability. Now, if you think you've got a monolithic application, you just single website, and you manage an uptime of 99.7% on that application, that's pretty good. That means your downtime of your system is about 1 day cumulative over a year. But if you have 10 microservices with 99.7% uptime, you don't get the same level of availability because you've now got 10 days of outages spread across your system, which, as a worst case, if any one microservice going down takes out your whole system, leaves you with only a 97% uptime, which is comparatively quite a lot worse. So one of the key things you have to get right when doing microservices is isolating them from each other and making sure that they can work without every single service in the system being up and running 100% of the time. Otherwise, you're going to end up with a lot more downtime in your system. One of the other disadvantages you can quite end up happening is knowledge siloing. Quite often you will find that companies that have microservice architectures will have teams that work on particular services, and they'll be separated, and it'll just be like, well, that's the user service team, that's the account service team, and that's like the notification service team. And because it's a small code base, it's probably only a small number of developers, 1 or 2, and maybe a shared product owner or business analyst across a couple of teams. But that can obviously end up with concentrating all the knowledge about how a particular service works with 1 or 2 people. And if that person then leaves your company or gets moved on to promoted to CTO or something like that knowledge leaves with them. So one of the things you need to do if you're running microservices is try and keep developers working on several different microservices so you don't get like knowledge trapped in one person. Another disadvantage is that testing the system as a whole can get quite complicated. Now, obviously, if you've got a single service, you're running unit tests against it, you're running integration tests, and you've got a really nice test pyramid, I hope. That's quite easy to do on a single system, but once you've got several systems which are interacting, there are a lot of combinations of different things that you might have to test, and that can sort of increase exponentially with the number of services you have. A bit later on, we'll have a look at one of the problems that you can sometimes run into with testing of how different components and how different services interact with each other. And quite often, when people are designing microservices, they forget to actually build a layer of integration tests which test the whole service. So you end up with, you've probably seen the image GIFs floating around on Twitter and things like that with like 2 windows that independently open, but as soon as you try and open them together, they've been installed in such a way that they hit each other. That kind of thing. You can end up running into that kind of thing with microservices as well. Orchestration of the system is also quite difficult. Obviously, if you've got a single microservice, you set it up, you load up your your browser points to a single sort of endpoint. You've got maybe Nginx or Apache running a web server, and it's just going a single path through your infrastructure to the system and to the database and back to the browser. If you've got lots of microservices, you've got a lot of moving parts, you've got a lot of different configurations. Each microservice might need like different environment variables to talk to external services or databases. You're going to have maybe different deployment constraints on particular microservices depending on how they need to operate. So And you also need to have an ability for microservices to find where each other is in your stack. So if you've got a service which needs to talk to another one, it needs to be able to find it somehow in your infrastructure. So you're going to need to, if you're building microservices, you're going to need to invest quite heavily on the automation side to get those deployments right every time, using things like Terraform or Chef and those kinds of tools. So one of the things I've not touched upon yet is this idea from the talk title of a distributed monolith. Now, when you're building a monolith application, there's a lot of architectural mistakes that you can make where you introduce coupling between different parts of the application, and you get away with them a lot more because the way that a monolith works, it's all in a single executable, it's all in a single code base. You don't notice the problems that are caused sometimes by modules just calling each other all over the place. You might find that some of these problems cause you bugs when you're adding new features and things like that, but a robust test suite can sort of fill in the gaps and things like that. But when you make some of these mistakes in a microservice architecture, they can lead to a lot of very difficult to diagnose problems. I mean, even the least worst thing that can happen is just the whole system itself is very sluggish and slow. And what this is sometimes referred to is a distributed monolith, where you have the advantages of neither architecture and the disadvantages of both. So I'm going to cover a couple of the common issues that I've seen. Probably the number one mistake I've seen when people go to microservices is something that I call the common library. We do maybe a quick show of hands. Has anybody got some sort of form of microservices, service-oriented architecture they're currently running right now? We have a few people. Yeah, I see a few hands. A bit bright, but yeah. So keep your hands up if you've got a common library that you sort of, yeah, I see a couple of people admitting to that, that's good, yeah. So the reason for it being a common mistake, it's partly due to the way it comes about. You think it's a sensible idea, okay, we've got these shared functions that we use everywhere, we'll just group those into a common library, so you can speed up development and deployment of new services. And the effects that a common library has on your development speed in your system take a long time to show up. And something that was an advantage at the start and gave you speed and agility starts to slow you down. So you start building up a body of code inside a common library, your microservices start to lose their independence. It starts as a minor inconvenience. You need to implement a feature in a microservice, and you go, well, actually, we need to change something in the common library to support that. So that means you're working on two libraries in parallel. You've got to put two pull requests in. You've got to coordinate the merging of two pull requests. But then it really becomes apparent when you make that change, deploy it, everything's good. Your stakeholders are happy with the change you've made, and then a week later you deploy an unrelated microservice. It doesn't work with the updated version of the common library, and it breaks. Your common library being shared between most of your microservices means that it becomes kind of a bit of a dumping ground for anything that you need to share between at least two microservices. And your small, lightweight code bases suddenly have this huge, big anchor that they're dragging around with them. So your advantage of having developers that are okay, we get focused on a very small piece of system, also have to understand this huge common library, half of which might not be relevant to the microservice that they happen to be working on. And you start bloating up a code base with a lot of unused functions and classes. Oops, gone too far. Common libraries can become quite unstable. When you've got a lot of microservices and they're all depending on functions and classes in there, you can end up changing that library very rapidly. You end up without a proper versioning structure, so you're just depending on dev master, and that then reduces the reliability of your builds because you can pull in a potentially under-tested dependency at any point in your build process. And it makes using Composer quite awkward as well, because you don't get the advantage of the subversion things. And it discourages technological diversity. So if you've got this nice big common library that's got a whole bunch of functions that everyone's familiar with using over and over, if you want to say, well, okay, actually, we want something that's written in Go for this particular problem, you have this common library and say, well, if we try and build a microservice in Go, we're going to have to build this whole common library in Go as well, because that's what we use to build our services. So it gives you this kind of almost a mental block on, oh, look at how much work it would be to introduce a different technology into our system. So how can we solve this? So instead of creating a single kind of common library that's filled with everything under the sun, try and keep functionality into smaller, focused libraries containing only a single piece of shared functionality. That way, only the microservices that need to pull it in. It'll change much less often, and a small library is much easier to port and reuse if you decide that you want to build something in Python instead of PHP. You might find this worsens the multiple pull request problem. However, with smaller focus libraries, it's much easier to find the new feature you need to build, realize that you've got a change in your small library, build a new version of it as a separate work piece, get that all tested, deployed, merged, everyone's happy with it. But because you've got a small library, it's nicely versioned, no one pulls it in, and then you can then proceed to work on your microservice change where you update the version of the small library and proceed to make the change that you need to make. That way, obviously, you only include what you need in a particular microservice, reducing the bloat, the unexpected surprises when you change things, and also the overhead for a new developer getting in on the project as to what they need to get a hold of and learn, essentially. Obviously, when you've got a lot of libraries, you're going to need to use Composer to sort this out. When you start managing lots of these things, the first thing you're going to start doing is you're going to put repository links in your Composer JSON. With a link to the particular repository that you've put your private package in. But as you start to scale and have lots and lots of these, that gets a bit overwhelming. So you probably want to start looking into either the sort of running yourself packagist, which is Satis, or you want to help the Composer people out and subscribe to their private packagist service. They'll do all of it for you, and you sort of obviously help to contribute to the maintenance and development of Composer as well. And sometimes you just have to copy and paste. This is kind of contrary to a lot of programmers' core instincts, because you want to make nice reusable things. But sometimes just copying and pasting the piece of code you need from one microservice to another is the safer and cheaper option. It allows an initially shared code between two microservices to evolve independently without risking the stability of the other service. Instances where I've seen this work quite well is if you've got something like an abstract controller class with some helper methods and things like that. And you use that across a few microservices, but if you give each microservice its own copy, then it can evolve independently and you can have microservice-specific methods in that abstract. Another of the problems I've encountered is when you have interdependent deployments of microservices. So quite often you'll have a change in one microservice, and so you've deployed a new API or changed to an API in it, and that means that the three microservices that rely on that API also need to be deployed at the same time, the same change. I've come across this in a lot of ways, and sometimes it only occurs very rarely. Sometimes it happens very often. I had a client that I worked for where the microservices would only work if you, in the development environment, if you scaled them up in a particular order, which was a bit interesting because it wasn't documented. That took about a week of some very expensive contractors' time, to figure out exactly what the order was and how to get them to run. So obviously, I'll give a bit of a live demo, because it's a problem that's best demonstrated visually. If you've got a single deployment, you can do quite a lot of fancy things to deploy your microservice. But as soon as you need to deploy lots of things at once, things go wrong. And as you see, you can kind of drop the ball and make a mistake doing the deployment, which leads to downtime. Now, if that wasn't bad enough, just think if you're having to do that at 3 AM in the morning when you've had a bug, you've got an emergency fix to a production issue, and instead of just regular juggling balls, they're also on fire. I've been told I'm not allowed to do that in here, fire regulations or something. Each simultaneous deployment increases the risk that something is going to go wrong and that you're going to make a mistake. You've got more to concentrate on, and it requires a lot more sort of QA time and developer time to make that deployment go smoothly. It also increases the pressure to skip over important items, such as thorough testing. If you've got to deploy 5 services, you're not going to be able to spend as long testing each one went correctly. And what happens when you need to roll it back? If you've got 5 deployments that you need to do at the same time, 4 of them worked perfectly fine, and then the last one, oh dear, what happened? Oh, we need to roll everything back. So you've now got to coordinate the rollback of 4 services, and you can't just immediately roll everything back and get back to a working state. It's going to take you additional time to roll back each service and get back into a working state. So what's the solution? So probably the first and most obvious way to avoid this problem is by versioning the APIs that your microservice exposes to the rest of the application. That way, when you release a new microservice version, you can leave previous versions of the API available so that your other service can choose what they want to use. Now, one of the ways I've done this quite often in the past is we needed to rename an API endpoint, and it was being used by several other parts of the system. So the way we did this was we made a copy of that new endpoint under the new name, under the new root. And then after that, we deployed that change out, leaving the old one in place so that any application that consumed that API could use either the old or the new one. Then we pushed out changes to the new services, the ones that talk to it, and updated them to use the new URL. And then finally, we did a third change to the original microservice to remove that old endpoint once we knew that everything in the stack had finished using it and no longer touched that endpoint. And that way, we reduced the dependency of having to deploy everything at the same time. Feature flags. It's kind of a similar idea to the staged API endpoint. Is what you can do is you can put a flag into your code that says enable this feature that breaks things, and you can deploy your code out with it switched off initially. Once you're happy that you've deployed all your services and they're all stable and working and you don't need to roll anything back, you can then very quickly, using an admin panel or whatever it is you use to manage your feature flags, turn it on across the whole stack in one atomic action. And then obviously if it doesn't work, you can roll back, you can just turn the feature flag off. So you've got this like 2 steps to your deployment, one where you deploy the code, and then the next where you actually enable the new feature across your entire infrastructure. The final tool you have in your box to help against the deployment coupling is automation. Now, even with the best designs in the world, you sometimes end up with a situation where you have to deploy 2 things or more at the same time. If you're in that situation, having good deployment automation is absolutely essential. You need to be able to click a button to deploy something and click a button to roll it back and have everything handled by scripts and automation. Although I would say this is kind of a last resort. You really want to, before you end up with a situation like this, you want to start thinking through how can we break this change down into multiple independent steps. That'll work so much better for you. Now, the previous problems I've gone over, the independent deployments, common libraries, they're pretty well contained. Once you know what to look out for, because you've been watching this talk, and you know the strategies to manage the issues, they're quite straightforward to handle. However, the next few issues that I'm going to go over crop up in even the best design systems and can quite often be impossible to completely eliminate. The first of these issues, race conditions, are probably my least favorite problem. Even sort of discovering them and finding them in a code base is hard. And then, once you've actually figured out that you have a race condition, you then have to diagnose and resolve the issue, which can be challenging, as replicating an issue locally often requires precise timing or very specific conditions. And then, once you think you've fixed it, you've got to kind of hope that you did actually fix it, because it's really difficult to actually replicate the precise timing that you need. So it's kind of often just a shot in the dark. So a race condition occurs when two competing processes, or two competing microservices, two competing users, try to interact with the same resource at the same time with conflicting intentions. The end result would differ depending on which process completes first, or wins the race. Now, in a system that's functioning correctly, that handles race conditions properly, the process that finishes first should win outright. And it's whatever it was trying to do is done, and whatever the losing process was trying to do should get rejected as invalid, and they'll have to sort of reload the page, try again, or refresh the data and make new calculations. In complex systems, this very often does not happen correctly, and you end up with a complex state. A simple example of this might occur if you've got two users, and say one's using your web app and one's using the mobile phone app, and maybe they have two slightly different paths through your code base, because one's interacting with an API and one's interacting with a sort of more controller form-based type thing. And you've got one item left in stock, and both users simultaneously try and add that to their basket. Now, if your system's performing correctly, it should end up with only one user with that item in the basket. But if you've got a bit of slightly different logic in each sort of path through, you might end up with a bug, in which case both users end up with that item in the basket. And when you come to try and debug that, as a developer, you look at it and go, well, how on earth could that happen? We've got like a check here. It says if item is out of stock, do not allow it to be added to the basket in both sides. And you're like, well, how did this occur? And the reason is, when that code happened sort of interleaved at the same time, both parts of the code managed to check and say, yes, we have that in stock. And because it was happening at the same time, you hadn't yet removed the item of stock, so it ended up in both baskets. Race conditions are a wild, multi-headed beast. I don't think I've come across two race conditions which are presented in exactly the same way. And I've even found them in monolithic applications, where you've got two users or a single user with multiple tabs open interacting with something. But in a microservice architecture, it's not just your users you need to worry about. Interdependent services can also cause race conditions when they're trying to update the same resource. Probably one of the most annoying examples that I had recently was we had a service which we were replacing with a brand new API with a legacy system, and then there was a third service. And the piece of functionality that we were working on was creating a new account in the system. And what needed to happen was we needed to make an API call to the third microservice to tell it that the new account had been created. It did a bit of work and then called back into the legacy system to say, hey, I've done this bit of work, here's some IDs you need. And what we did, we had this new shiny system, everything was wrapped up in a transaction. So when we saved So when we made the API call out, the transaction was still open, and the account hadn't yet been committed to the database. Most of the time, that'd be fine. We dispatch the command to the service, it would do its thing in the background, we'd commit the transaction, it would be fine. Very occasionally, that service would go really, really quick, and it would call back into the legacy system before we had committed the transaction and created that account. This would then cause the legacy system to go, oh, that account doesn't exist, and create a brand new, blank, empty one, which would then cause a transaction to fail to commit. Diagnosing that was, yeah, it was a nightmare. Yeah, so we eventually got to the bottom of it, but it was a bit like fighting this beast on the slide. I'm going to go on to the next issue, as kind of like the current grouping of issues have very similar cause and kind of effect. So we're going to go over the solution like all in one go. The next issue that I've encountered a few times is what's described as temporal coupling. Essentially, the problem is when one microservice has to talk to another service, and then it needs to wait for a response from that service before it can continue its task. Now, often you have some sort of orchestrator service or gateway that calls out to one service, waits for a response, calls out to another service. Let's have a look at an example. Consider this ticket booking application, which is comprised of a group of microservices. Now, when a user wants to purchase a ticket, they submit a form with their card details, the number of tickets they want to buy. The server application, the orchestrator at the front end, then makes calls to the user microservice to check their login and retrieve the user details. And then the ticket microservice to check that the ticket is actually available and there's enough for the user to purchase. The fraud microservice to make sure that the card detail isn't reported stolen or anything like that, or it's been implicated in fraud. It then calls the payment microservice to actually take the payment with those details, and then goes back to the ticket microservice to record the tickets as sold. The accounts microservice to record the sale and log it in your accounting system. The loyalty microservice to update the customer loyalty points. And then finally, the email microservice to send an email saying thank you for your purchase. Now, in every one of those steps, your sort of orchestrator needed to wait for a response, get some details back, and then try and coordinate between a lot of different microservices to do what should be a fairly straightforward action of booking a ticket. That is a distributed monolith, in effect. It is a single function that is spread across lots and lots of different microservices. Now, what makes this so bad is performance. First of all, the first thing you'll notice about this kind of setup is it's really slow. You have lots of back and forth, probably over HTTP REST requests, even if they're pretty quick because they're in the same server stack. You're still going to put a lot more overhead. If you call in a method in PHP, you're measuring the amount of time it takes the system to call that in microseconds. Whereas a network call can be measured in tens or even hundreds of milliseconds. That's up to 100,000 times slower. So if you're making lots of calls out to different microservices, you're adding a lot of latency into your system. In the previous example, everything happened synchronously, so each service had to wait for a response from another service before it could continue. So even just a single failure in one of those microservices brings the entire process to a halt. If your fraud microservice has gone down for maintenance, you cannot do a fraud check, and you cannot service any ticket booking requests. The whole thing has fallen over. And what happens when something goes wrong? The number of failure scenarios grows exponentially with each additional service involved in an operation. For example, at any stage, some business logic could fail. If the tickets are sold out, the customer doesn't pass the fraud check. But you could also have infrastructure issues. If you have connectivity problems between one of your microservices, or one of them's overloaded and is being very slow in returning responses and timing out. What do you do in those situations? If you make a call out to the ticket booking service saying, hey, we've taken a payment, mark these tickets as sold, and you don't get a response, what do? Do you try again? Did the ticket microservice receive the response but just take too long to process it before your connection timed out? Did it not receive it? Was it down? Was there an error saving the result to the database? There's no way to know what went wrong once the request has left your service. So it's really difficult to know what to do about it. The commonality between these last two issues is that they're both situations in which a single operation crosses the boundary of several different microservices. And crucially, we want that operation to succeed completely or fail completely, essentially a distributed transaction. The success path of this situation is usually really quite simple. Each service in that flow, if it did the thing it was supposed to do correctly, first time, promptly, that'll work really nicely. It'll work, and you'll book a ticket. But when you get to error situations, each additional service that you involve beyond the first becomes much more complicated. Even the case for just two services is really tricky to handle. Now, there are strategies to deal with this, such as a two-phase commit, but the complexity of that solution scales exponentially with the number of services involved. And in a microservice architecture, you can have sometimes hundreds of services involved in your system. So if you're trying to do a two-phase commit across lots of them, you're adding even more latency and even more overhead to the user's request, and your system becomes a lot more sluggish, especially under load. Distributed transactions are really, really hard. Because obviously, in the event that we have an error, how do we even handle it? If we're partway through doing a ticket booking, we may need to coordinate with multiple tickets. You know, if you put a hold on some tickets and you need to roll back because a payment failed, you then need to make a call to the service to release them, but then what happens if that call fails? Because you don't just necessarily have failures when you're trying to do the operation in the first place. You might also have failures when you are trying to recover from your first failure. If at all possible, you really, really, really must try and avoid doing distributed transactions. So some of the theme of all these problems I've been discussing, they're all examples of coupling between your microservices. Just like you have a lot of talks about decoupling from frameworks to improve your development processes, tight coupling between microservices is also a major source of problem. And it will slow you down, it will cause bugs, it will cause problems on your system. And so you need to avoid coupling as much as possible. So some potential suggestions: avoid microservices which are too small, nano services. There's often a misconception that a microservice needs to be really, really small. I've heard horror stories of people talking about a Java system where each microservice was a single Java class. Now, I'm not sure if they were exaggerating or not. I really hope they were. But that kind of layer of granularity is way, way, way too small. You're going to run into so many problems with doing things like that. So it's absolutely fine for a microservice to have a fairly broad responsibility, provided it is focused on a single business function. You can also have a UI in your microservice. I have built systems where each microservice produced its own user interface and handled all the UI stuff as well. So generally, you would only be going to one microservice for everything to do with an operation. Define clear boundaries between your microservices. The clearer the boundaries, the less they need to communicate with each other. It should be possible for, in 95% of your operations, a single microservice handles the initial part of the operation. So when a user makes a request, it doesn't need to talk to another microservice to complete that request and return a result to your user. Now, these boundaries are really hard to get right up front. So that's another reason to keep your microservices quite large to start with, because it's much easier to break a service down if you decide it's too big And you can say, well, okay, well, we've clearly got this small bit of functionality over here, which could go in its own service, because it's kind of separate from everything else. It's much easier to do that than it is to go, you know what, we need to stitch these 7 services back together because they're all interacting with each other all the time. Another thing you can do, and this is what we're going to talk about for the last 10, 15 minutes of this talk, is to communicate asynchronously between your microservices. So instead of using a REST API, you use a message bus, such as Kafka or RabbitMQ. Now, this can require a bit of a shift in thinking, so I've got like a bit of time dedicated to it. And so what we're going to be looking at is a technique called event-driven or message-driven architecture. In brief, the idea is that instead of making API calls via HTTP to your services, you instead communicate with your services primarily through an event queue, a message bus. You might sort of recognize this idea, representing state changes as stream of events. I've given talks in the past on event sourcing. You can look them up on YouTube if you're interested. And there's a lot of overlap between the techniques you use in sort of message-driven architecture and in event sourcing. But the main difference is scale. Event sourcing focuses on a small model in your system, a single model, whereas message-driven architecture, you're looking at state between services. And it isn't necessary to do like event sourcing like all the way down the stack. And even if you did, you'd probably have different events and different messages being exchanged between services as you capture within your models. So let's have a look at what it would look like. So our previous example, our ticket booking system. In this architecture, we attach all those microservices to a message bus. Whenever a microservice processes some user input, which causes a change that we need other microservices to know about or react to, we publish a message to the event bus. And each microservice listens to that bus for messages that it is interested in. It will then update its own internal representation of that message, and potentially it might discard some information that it doesn't really care about. Some of the accounting things probably only relies on what the pricing information is. It doesn't really care about like the venue of the ticket and things like that. It may also, when it processes it, publish new events to the event bus as a result of the processing that it's done. We take a simple example of the booking a ticket again. When the ticket microservice handles a sale, and notice that one of the things I've changed in here is to roll that payment service into the ticket service so that a user can complete a ticket booking flow entirely within that single microservice, payments and all. Once that sale is completed successfully, and only at that point, we publish a message to the event bus. Then we have several services that are interested in, hey, we've sold a ticket, we need to send an email confirming it, we need to update the user's loyalty points, we need to do a fraud check, and we need to log it in the company accounts. They implement their own logic, and then maybe as a result of the ticket purchase, the user's loyalty tier has increased from silver to gold. Great. And so the loyalty service publishes another event onto the message bus, and that's picked up by a couple more microservices that then do their own thing related to that. So the user microservice updates the loyalty tier to gold to display on the web page, and the email service dispatches a, hey, welcome to gold tier. Here are your new perks and benefits. Now, one thing I haven't covered in that example is what happens when something goes wrong. Now, you'll notice that we've managed to eliminate a lot of the failure modes that we had in the original architecture. We no longer need to worry about what happens if we can't make a direct call to the loyalty service to update the user's points. But there's some situations in where things might still go wrong. For example, if a transaction is flagged as fraudulent. In this system, because we're not doing it in real time, we can't rely on that check to happen before the tickets are booked. So when the fraud service sees the ticket booked message and checks it and goes, oh, that's a bit dodgy, it it can't just like say, no, don't book those tickets. Instead, it has to issue a compensating message to the bus. It says, hey, you need to block that purchase. And so it'll issue an event, and the ticket microservice will pick that up and go, oh dear. And it might put that order on hold. Now, one of the interesting things about this is that it's not necessarily a rollback. You get a compensating event onto the bus. You don't necessarily have to just undo everything you just did. You might do a sort of asymmetric action where you put the ticket booking on hold, and then the email service goes, hey, hold on a minute, let's send an email to the customer, get them to get in touch with customer services and sort this problem out. And only after, say, a few days, if they don't contact them, then the ticket microservice might say, okay, well, we'll cancel that purchase off entirely and release those tickets back into the pool for sale. Of course, you might be thinking that previous example is a bit absurd. You'd think, well, something as important as a fraud check can't be done in an eventually consistent manner like that. We need to know in real time if a particular transaction is fraudulent so we can block it. So we don't incur problems with our reputation with our credit card provider. But obviously, there are some things that you don't necessarily need to do in real time, like updating the loyalty points. A few seconds delay on that isn't going to be a problem. So when you're thinking about this message-driven architecture, it is okay to trade off and say, well, actually, some things we do need to do in real time. And you can still use a REST API to communicate between your microservices, even if most of your communication happens asynchronously on that event bus. If you're going to do this, and it is a bit of a trade-off, you're trading real-time responsitivity for some of the disadvantages like availability and things like this, you can limit the problems that occur if you limit the synchronous comms to two situations. The first, where you're doing a read-only action, so you're asking a question. You're saying to the fraud service, hey, does this payment look dodgy? And the fraud service can give you an answer back straight away and go, yeah, it does. The other time is when you might be telling a service to do something, but you don't care about the response. An example of this I came across was setting with direct debit. Now, we had a service that dealt with communicating with banks and setting up direct debits, but it took about 3 hours to get a response back from the bank. So we could tell the microservice, hey, set up this direct debit, and the microservice could validate the bank details were sensible immediately and respond back and say, hey, yeah, that's all cool. That looks like it's gone through okay. But then we wouldn't know back from the bank if we'd actually managed to set up the direct debit for a few hours. So we couldn't get a result, and we didn't care about it. We just needed to know that the service had accepted those details. So that's another case where you might trade off and do a real-time communication. Another thing I mentioned is that we've eliminated downtime as a failure mode. That's not 100% true. Because if a service goes down, although it won't impact the other microservices in your system, they might find themselves missing important events while you are fixing whatever problem has caused them to fall over, or you're completing a complicated deployment. And so a bunch of users might book tickets and they've missed out on their loyalty points. Now, the best way to handle this is outside of your usual queue of events. If you have each service which is publishing events to the event bus, keep a copy of every event that it publishes and assign it like a unique ID and an ordering. So like a timestamp or a numeric ID that increments. Then, if you have downtime on your loyalty service, what happens is, as part of the boot-up process of the service, it can say, well, I really need to know about any ticket sales that happened while I was rebooting. So it can make a call out to the ticketing service and say, hey, I've seen events up to event number 475. Have I missed any? And the ticket service can obviously respond back with a JSON blob saying, hey, yeah, here's events number 476 through to 490. And the microservice can process those and then boot up and start listening to new events being published on the event bus in real time. So some of the advantages of this event-driven architecture is it decouples microservices from each other. That means that they can focus on performing their roles and telling others about what they've done, rather than relying on other microservices to help them out. It allows for a small amount of microservice downtime without a great effect on your frontline service to users, because if a failure anywhere in the first model that we had would prevent any users from booking tickets, whereas a failure in the message-driven system can probably be recovered from just with a bit of lag on maybe sending emails or doing loyalty points. It scales really quite well. If you've got a lot of spikes in activity, your message queue will just buffer up events for you. So if your email service is under a lot of stress, because it's sending out a lot of emails, it can just sit there and process in the background, and you're not having to scale it up to cope with a huge influx of tickets that just because something's just gone live. You know, a brand new, very popular artist is putting a concert on, your tickets have gone live, your email service can't cope with sending out all the confirmation emails. Now, if you had a synchronous communication, you'd have to scale that up alongside your ticketing booking service. So again, you're losing that scaling independence. Whereas with your event-driven architecture, you've just got a whole bunch of messages in the queue, and you know, when the hotspot, you know, when the ticket booking spike has finished, the email service will eventually catch up and get those emails out for you. It's easy to change the system. If you have a new microservice that you want to add on, you don't need to have the other services, you don't have to change the other services to make them aware that you've added a new auditing service, for example, that audits ticket sales and payment details and things like that. You can just attach it to the bus and it can start listening to messages. You don't need to go into your other microservice and say, well, okay, well now we need to add a call to the audit microservice to log the purchase. And if you've got your event endpoint to replay the event, when the audit service comes online, you can just grab that list of historic events in the very beginning, start it all up, check your code works, bring it online, and it makes it a lot easier to change and bring new things in. You also get rid of those distributed transactions. You don't need any of the handling logic because you model your failure cases and rollbacks directly into streams of messages and compensating actions. So you explicitly say, well, you know, okay, if something goes wrong here, we'll just publish an event that says something's gone wrong, and we can take a compensating action. The latter option is going to have much better customer service implications, because like if your email service goes down, for example, or a payment fails, you can have your customer service team say, well, okay, well, the payment failed, and you can get in contact with that customer and say, hey, your payment failed. We saw that after the fact. We said you'd, you know, you booked the tickets. You've got them reserved. It's okay. You're not missing out on Taylor Swift or whatever artist it was that they were trying to book. But we need to get new credit card details because the payment was declined. So you can actually produce a much better customer service response to the things going wrong as well, which will have a lot less complaints from your customers. So, we're getting really close to time. I'm going to stop people getting for lunch. I had a brief look at microservices and monolithic architectures and why you might want to use them. I've also covered some of the common mistakes that people make. And finally, we looked at how we can use asynchronous communication to improve autonomy of microservices. I'm going to very quickly, because I am now standing between you and your lunch, go through some of the key takeaways. So, you know, if you want to take a few photos and things like that, this is probably the time to do it. So every architectural decision that you make is going to involve some trade-offs. One of the important things to take away from this talk is to know what the trade-offs are so that you can make an informed decision about whether you want to actually embrace microservices or if you want to stick with a monolith. Some of the trade-offs are clearly worthwhile, while some may be made because someone who's close to the problem goes, well, I've done microservices before, they work really well, they're going to work really well here. And you can sometimes get stuck in a track of being like, well, this has always worked for me, this is the way I do it. The choice between monoliths and service-based architecture it involves trade-offs. Start big. It's a point that bears repeating. Microservices are so named because they are micro in comparison to the monolith that you're replacing with them. It's not a judgment on the specific size of the service itself. And it's always better to start off with a big microservice and split it down as you learn more about the problems that you're solving, and you can make better decisions about what the boundaries between microservices are. If you already have a monolith, it's actually an excellent place to start. Find a self-contained area of the monolith and break it out into a new service. Continue with this until you have a microservice architecture. Favor autonomy over the single responsibility principle. Many of the problems you run into comes from a high degree of interaction between different services. This can come from really overzealous enforcing of the single responsibility principle. You say, well, okay, that microservice is only responsible for this specific thing, and so if we need a different function, it needs to go over here. But if those two functions are very closely related and interdependent, it's much better to just stick them in one microservice and kind of fudge your single responsibility principle a little bit. It's a worthwhile trade-off because it stops you from having all those interdependent coupling between two microservices. And you've always got the option to break it out later once you evolve the design to reduce the coupling between the functions. And the final thing is perhaps a more controversial point, but embrace eventual consistency. If you are building a microservice architecture, it's a great way to save a lot of headaches. The real world is eventually consistent. Now, if you've got a computer system which says, hey, you've got 10 TVs in your warehouse, and you sell one, and the computer system says, okay, there's 9. How many have you got available to sell? It's not necessarily 9, because unbeknown to you, last night someone broke in and nicked one, and also when they were unloading the lorry last week, someone dropped one and it's broken. So you've actually only got 7 that you can sell. But your computer system doesn't know about those two actions because, well, it's not linked up to the security system, and the staff member shoved the broken one at the back of the rack and hoped no one would notice. So if you end up selling too many TVs, your system's going to be wrong. Business processes were eventually consistent before they were computerized. You know, if you had a process which an office followed to complete an order, it would be a piece of paper that was passed around, different departments would stamp their piece on it, and it would go into people's inboxes and in trays, and you wouldn't have a system which was 100% consistent all the time. You generally don't need that level of accuracy in your system, and you can take advantage of that when building microservices. Okay, well, thank you very much for attending the talk. I hope you found it useful and interesting. I've got my Twitter handle, and yes, I'm still calling it Twitter, and also Mastodon on there if you want to kind of follow me on there. I'm not particularly active on there, but yeah, sometimes. And then there's my GitHub and sort of kind of blog on there as well. So if anybody wants to sort of check those out, they can. Otherwise, I will let you all get out to lunch and have a good lunch. Thank you very much.